Let's continue the construction of ILD by using Muller-Brussel's principle. Now the ILD for up to RA we have seen, RB and AC we have seen. Now ILD for MC. So according to the Muller-Brussel's principle, we have to introduce a unit displacement in its own direction. So we have to release the bending moment here, means we have to put an internal hinge. So this is just like, so we are connecting two bars at C by an internal hinge and we are allowing to rotate them. So that means, and through unit rotation, that is this theta 1 plus theta 2 equal to 1, or we will write here theta 1 plus theta 2 equal to 1. What is theta 1? Theta 1 is nothing but h by a. Actually tan theta 1 equal to h by a. Since theta 1 is very small, so tan theta 1 equal to theta 1, which is h by a. So this is h by a plus, what is theta 2? It is h by b. Tan theta 2 equal to h divided by b. Since theta 2 is small, therefore tan theta 2 equal to theta 2. So this is h by b is equal to 1. So you take h common. So this you will get a plus b upon ab equal to 1. So what is a plus b? A plus b is L, total span. So therefore h you get ab upon L. So this ordinate ab upon L, and by calculations already we have calculated this ordinate. Now next, see these are the ILDs for simply supported beam for various structural function. Now let's consider second example is a cantilever beam. Say let's consider a cantilever beam. Now use Muller-Brussel's principle only. Say this AB is a beam, RA here reaction, MA is the moment, and L is the span. Say let's consider a section C at a distance A, at a distance B from right hand, and total span is L. So now first construct ILD for RA. So ILD for RA. So remember, the end A is fixed and B is free. If I lift, so keep fixity as it is. So don't release fixity. Only vertical deflection is allowed. Now I want to lift this up. So what will happen? The free end gets lifted because fixity is there. So that means it's a constant. It's a constant. So this is lifted up through unit. So here it is 1, here it is 1. RA is to be lifted through unit. So simultaneously the end right hand B also got lifted up. So this becomes ILD for RA. Now for MA, what we have to do? For MA, introduce a hinge here. See, if I introduce the hinge, if it is a cantilever and rotation is allowed, so what will happen? It will come down and it remains straight. So just come down. So no, because vertical support is there. So this vertical deflection is not allowed. Only rotation is allowed. Allowed to rotate. So it will come down. So, and this will be, if you want this as a 1 degree unit displacement, 1 radian, 1 degree unit displacement, then if this is L, this must be L. To have that unit rotation, the height must be equal to the base. Now let's consider the section C. Let's consider the section C by using Muller. Already we have constructed all these ILDs by using the calculations, by establishing the relations between the structural function and position of moving unit load. Say, now here shear means we have to take a cut section here. We have to cut at C. Shearing, total sharing should be unit. Say, but remember this end is fixed, so it will remain straight up to this. We have taken a cut and the right only gets lifted up by calculation. That's why you just keep the shapes of the ILD for cantilever and simply supported beam in your mind in order to understand this is 1 and this is positive. So this is MA and this is SC. In order to understand the ILDs for shear force bending moment at any section, see that whether your section is within the simply supported span or whether the section is within the cantilever. If it is within the cantilever, the shape of the ILDs just observe will be like this. Now bending moment, MC. Again this is fixed, will not disturb, so bending moment here is to be released. So introduce a hinge here. Hinge means here rotation is allowed. But left hand side will not be disturbed because there is a fixed support. These supports are fixed, will not be disturbed at all. So therefore, and negative sign because this is cantilever, so as per our sign convention, if this base is B, the height must be B because we have to allow rotation 1. In order to have unit rotation, base and height must be same. So these are the ILDs we have constructed for the simply supported beam and cantilever beam by using Muller-Brussels principle. Now let's solve some more problems, some complicated problems by using Muller-Brussels principle only. Now as far as influence line diagrams for beams are concerned, or determinate beams are concerned, plotting ILDs by using Muller-Brussels principle is very, very interesting and again very simple. So any type of beam that we will see, now suppose we have a beam like this. Say this is AB and this is CD, AB and CD. Say this is A, this L, and say this part is B. Right? Now, what are the possible ILDs here? That is reaction RA, reaction RB. So construct ILD for RA, RB. Then next, what I will do, so let's take the sections, say this one at a distance A here and remaining distance B. Or use any other because say AB overhangs we have taken here. So instead of AB, what we will take? We will take this known distances here instead of AB. Say let's take this as a 10 meter, span 10 meter, and say this is 4 meter, this is 6 meter, and this you take say 2 meter overhang, and this side you take 3 meter. So let's take this span 10 meter, simply supported span, overhang on left side 2 meter, overhang on right hand side is 3 meter. Okay, now this you take a section, say you take one more section here at a distance 1 meter, remaining 2 meter. So I am taking this section at a distance 1 meter, section 2, 2. So what I want is to construct say RA, RB S11, M11, S22, M22. So ILD for RA, ILD for RB, shear reactions at A and B. Then ILD for shear force and bending moment at section 11 and 22. So it is very clear that section 11 is within simply supported beam and section 22 is within cantilever beam. Again, if you take in AC, that section becomes section in a cantilever beam. That's why if you remember the ILDs for simply supported beam and cantilever beam, just see where your section occurs. Now the first ILD, let's construct ILD for RA. What says Muller-Brussels principle? That give unit displacement RA in the direction of RA, deflection. If there is a moment, rotation. Now RA in the direction of RA, give the unit displacement. Now if we consider, say this, now supported like this, say, so it becomes like this, say this is your B, right? Do you understand? Say this one side, I am keeping this side supported, and if I lift this array, so it's a like a bar, it's a rigid scale, so a straight line you will find, but you need displacement here. If you want RB, lift this, so that remains straight. Means you have the 2 points for which you can construct BMD. That is, say this is lifted up through 1, this is 1. So lifted up means this will, and the another point you have this, because there is a support, no deflection. So if you draw a straight line this end to this end, so whatever you get, this say it should be a straight line, remember, not a curve. So this is negative, this is positive, this is also positive. Now this is ILD for RA. What we did, we only introduced unit displacement at A, lifted up at A, and keep the straight line with deflection at B equal to 0. The deflected shape itself is ILD, that's all. ILD is over, it's only 1 minute problem. Now what are the ordinates? If this ordinate is 1, use similar triangle. Say this ordinate, suppose y1. So this is y1 divided by 1. Height of this triangle, external triangle, height of internal triangle equal to base of external triangle, this 10 plus 2, 1.2 divided by, 10 plus 2, 12, divided by base of internal triangle, 10, so this is 1.2. This ordinate is 1.2. Similarly, if you want to find out this y divided by 1, this triangle and this triangle you compare. Base of this is 3 divided by base of this triangle is 10. So this becomes 0.3. This becomes 0.3. So this is 1. This we know. This we know. So by using Muller-Brussels principle, and other ordinates you find out by geometry or by using similar triangles. So these ordinates are to be calculated, remember, that is important. So this becomes your ILD. So ILD for RA. Now what we will do, let's draw ILD for RB. Means give the unit displacement here at B, and this point support deflection 0. So you join these two by a straight line. So what you get is, so I draw this way. So now, where is unit? This is unit. So this ordinate is 1. This we know. So knowing this, now this height divided by this height, this y divided by 1 equal to this 13 divided by 10. So what you will get here is 1.3, and here you will get 0.2. This is minus, this is plus. Very simple. This is ILD for RB. So we have plotted ILD for RB. Next, let's draw ILD for S11, shear force at section 11. Actually, knowing for ILD is for RA RB, so directly we will get that ILD, but use Moeller-Brussels principle. So let's write S11. Now S11 means, say this is the section within simply supported. Here there is a support, here there is a support. We have support here, we have support here, right? So we know the simply shape of the ILD for simply supported beam. Left is down and right is up. Say this is A by L, this is B by L, this is minus, this is plus, and this is 1. So this is the ILD for a shear force at a section within a simply supported beam. But we have cut the bar here, it remains straight up to the free end. It also remains straight up to the free end. Say this ordinates we have to find out. So this ordinates, let's calculate by using symmetrical triangle. Or see, suppose if you extend this, this will become 1. If you extend this, this will be 1. Like a SFD, ILD for shear force for RA and RB. See, that means we can compare this triangle and this triangle. So this height divided by, or say this triangle and this triangle you compare. This height divided by this height is 1. This divided by 10, so this is 0.2. And naturally you will get 0.3. So this is plus, minus, plus, and this is minus. So this is ILD for shear force. Say, means this should remain straight with deflection 0 here. This should remain straight with deflection 0 here. And we allow shearing unit according to Moeller-Brussels principle. Now next, let's say only simply supported beam. If you know the ILD for simply supported beam, say M11. Say M11 we know for simply supported beam is this. And this is AB by L. This is AB by L. Then further you just extend this up to the end. Because further it is a free end. Then say okay, you know this AB by L, and you find out this by similar triangle. Say we can use this one and this one. Say this is Y. Say this height, AB by L means we can find out this 4 into 6 divided by 10. So this ordinate will be 2.4 because this is AB upon L. Say that means this Y divided by 2.4 equal to this height divided by this height. This base is 2 divided by this base is 4. then this becomes y equal to 1.2. So this is 1.2. Similarly, if this is y, so you can find out y divided by 2.4 equal to 3 divided by 6. Again 1.2. 1.2. So you find out this because this height divided by this height equal to this base divided by this base. So this is ILD for M11. This is ILD for M11. Now plot ILD for M22 and S22. Next, this is not required. Now here, say this section S22. S22 is within a cantilever portion and left hand side of the cantilever, that section will not be affected, and shear force diagram for cantilever is a rectangle. And this is always unit plus. This is S22. If you take a section here, then this side only exactly same, but on the left of that section you will get. And next, say if you take here hinge, so this is M22. And this base is 2, this should be 2 because this is 1. This is 1. Shearing is 1, bending moment is 1. Suppose you have a section 3 here. This is say 1 meter and 1 meter. If it is, and that is also a cantilever section, S3. So section is here, so it's a rectangle only. Say 1 plus. Then M3. Then section is here. Say this is 1, this is 1 because this is unit rotation. So means just say where is your section, within simply supported span or within cantilever, and accordingly you plot the shapes of the ILDs. Means Muller-Brussela's principle helps a lot in order to construct the influence line diagrams without doing any calculations. Now one more ILD, suppose because there is a bending moment at B, there is a bending moment at B. Now the bending moment at B, we can draw ILD, MB or MA also. Say this type of ILD we get. So that means the ILD, bending moment at B occurs only when the load is on the cantilever portion. Otherwise bending moment will be 0. And this is 3, this is 3. So this is 1. And this is for MB. ILD for bending moment at support B. ILD for bending moment at support B. So whatever the number of possible ILDs we can construct very easily for any type of beam. Now next, one more problem. Say we have seen cantilever beam, simply supported beam, overhanging beam with overhangs. Now say compound beams. Suppose we have ABC is a beam, hinge C is given at hinge is given at C. Now how to construct ILDs for, say here RA, MA, RB, then I will take one section here S11, M11, then take one more section here S22, M22. Now the influence line diagrams for this 1, 2, 3, 4, 5, 6, 7 ILDs we can construct here. Say this is RA, MA and RB. Then I have taken section say 1, 1, section 2, 2. And distances, let us say, take this as a 4 meter, and this is, again take 4 meter. And this small, this distance is 2 meter, 2 meter. So this is our problem. Now, RA, use Muller-Brussels principle. RA is fixed. If we lift this RA, so up to this hinge, it gets lifted up. But here deflection is 0, but that is rotated, remember. Means because this is fixed, fixity is to be kept up to the hinge. Here it gets rotated. So this is RA, ILD for RA, and this is 1. This is 1. So this is plus. So this becomes ILD for RA. That this is fixed. When we lift, so this hinge gets lifted up, and at hinge rotation occurs, and since the deflection at B must be 0. So this is, just assume this is a mechanism. Two rigid bars connected by internal hinge at C, simply supported at B, and the end A is fixed. And what happens if end A is lifted up? And you draw the deflected shape of this mechanism. So will be the ILD. Now RA, what is ILD for RB? So RB is lifted up to 1. Here it is lifted up to 1. But at hinge it gets rotated. This is a hinge. So this is RB, this is plus. So hinge is there. This is fixed. So this part will not be affected, will not be deflected. Only it's simply when you lifted off, so it gets like this, rotated here, and this is, no angle is not, that deflection is 1. So ILD for RB is over. MA, you know, so ILD for MA. So here hinge is introduced, and say you will get here, then rotate at this, deflection here it is 0, and this is 8, the height should be 8, because this is 1. This is slope is 1. So this is 8. This is ILD for MA, over, ILD for MA is over. This is allowed to rotate, so hinge will come down, again deflection here must be 0. This is allowed to rotate, that B. B is a simple support, slope will be there. Then this is ILD for MA, RA, RB, MA. These 3 ILDs we have constructed. Let us come to the ILDs for S11, M11. So ILDs for S11, then M11. Will you draw, is it possible for you to draw the free body diagram? Yes. If you draw the free body diagram, so how the free body diagram here? So this portion, this is fixed, and this portion, this becomes simply supported. Remember.